Video, I'm going to demonstrate some biomedical applications of first order differential equations. Okay, in this example, we have glucose. Glucose is given intravenously, okay, and it's added, right, and it's used up by the body, okay. Now, the way that it works here is that the amount of glucose, let me close this up here for a second. Let A, T, okay, be the amount of glucose in the blood. Okay? And here, what happens is that the rate of glucose, or the rate of change of glucose in the blood, is equal to the rate that you add the glucose minus the rate that it's used by the body. Okay? So here's the thing. The rate that it's used, okay, is proportional. So this guy right here. So dAdt is proportional to the rate added. Now, how is it used by the body? Well, it's used by the body. The rate that it's used is proportional to, so equals K times the amount present. Well, what's the amount present in the body? Well, or in the blood, that's A of T. So the rate that it's used is proportional to the amount that's present in the body. So it's used, more of it's used as if you have more. It's used more quickly. Let me clean that up. Okay, so we've set up a differential equation that now we have to solve. And how do we do that? Well, again, there are two ways to solve this kind of differential equation. One is the separation of variables, and number two, integrating factor. Okay, how do we solve this differential equation? Well, let's start with separation of variables. Okay, I'm going to keep this really general, and then we'll do an example where we add the actual values for different rates that are added and solve for K and all that initial value problem stuff. But what I'm going to do first is I'm going to show you in general, not adding values to these parameters, how you would solve this. So if you have separation of variables, you basically don't have much of a choice. This is a constant, right? R add. So you have dA by dt equals R added, this is a constant, minus K A of t. And what am I trying to separate? I need to separate the A, amount added, from time variables, okay? Or the amount in the body, in the blood. A is the amount in the blood. So what I need to do is I need to go 1 over R added minus K A of t dA is equal to dt. So I've separated the variables. And when you use separation of variables for a first order differential equation that looks in this form, you need to use substitution. So, well, if you're going to solve it, we've separated the variables. We can integrate both sides now, and we have to use substitution. And we always use the denominator. So let u equals r, I'm going to go with just a. I'm not going to write too much. This is a constant, minus k a. Okay, a is a function of time. Okay, so that means if you take the derivative du by dA, okay, is equal to negative k. So that means that du is negative k dA, but I don't have negative k dA, I just have dA on the left-hand side of my equation. So what I have is negative du over k. That's what I have. Let me go with this color. So when we use separation of, let me just go back here. When we use u substitution here, we're looking for the things that we have in our equation, and we are replacing them with what we have on the left-hand side. So you see here, we have dA, we're going to replace with negative du over k. Look. You see? So we're going to replace what's on the right-hand side, okay, which is in our integral, with what we have on the left-hand side from our u substitution. The u substitute, what we have here on the right. So what we have is we have 1 over u, okay, and we have actually negative 1 over k du. And that equals, okay, if we take the integral on the right hand side, the integral of dt is just t plus some constant, we'll call it c2, because I'm going to get an integral on the left hand side here. Okay, so the integral of 1 over u du is ln u. Okay, so I have negative 1 over k and ln of u plus some constant, c1. That equals t plus c2. Okay. Now, what I can do, let me multiply both sides by negative k. Okay. So that gives me ln u plus c1 is negative k t minus k c2. Okay. And what I can do is I can start grouping these constants that are, these can come together, okay, into one, under one constant. So ln, oh, let me go back. I have u, let me put everything back. This is Ra minus Ka. A is a function of time, okay? I'm just reminding you that that's what we're looking for. Okay, and that equals negative kt plus, so we're going to have c1, negative k plus c2. I'm going to lump those all into here, into this constant. Okay, so this is very similar to what we've seen before, right? This is the ln form of the solution, of the general. This is the general solution. Okay, in ln form. This is the ln form. I have it in ln form. Okay, I can solve for a as a function of time if I just here's my base. Base of ln is e. So if we want to solve, we can find the other form. It's just Ra minus k a of t is e to the negative kt plus some constant. I'll call this c naught. How's that? Plus c naught, which, I mean, this itself becomes e to the negative kt plus times e to the c naught, and this right here is just another constant. Okay, so that becomes c e to the negative kt. Okay, so if I bring the kat over to the other side, I can go like this. Let me see. Okay, here, let me do it in a way that's easy to follow. K a of t equals c e to the negative kt minus ra. Okay, I'm going to multiply both sides by -1. Okay, and now I'm going to divide both sides by k. Okay, and so that's going to cancel. Now, a of t, this is the solution. It's negative c over k e to the negative k t plus r of a ra over k. Okay, the unknowns are c and k. These are the unknowns. Okay. All right. So we have the two form. This is the general solution. Let me zoom in a little bit. And it's just in standard form. It's in terms of A. Okay. If we had the initial values, we could solve, no problem. But that's not the whole point of this video. What I want to show you is that we can also use the integrating factor method. Okay, and let's go back. Let's go zoom in here. Let's do a review. Integrating factor. Okay, put this in the form that we, so I'm going to grab the equation here. We have this equation. That was our starting point, right? We started with this equation. I'm going to copy that, bring it down here. Okay, so this is what we have. Okay, the integrating factor method has these things. So if your equation, okay, let me zoom in here. Let's clean this up a little bit. So we got dy. If your equation is in this form, okay, then you need to find the integrating factor that you're going to multiply both sides of the equation above, okay, so that it looks like product rule. And when we did the derivation for this, we found that the integrating factor was determined to be like this. And when you multiply both sides of equation 1 by r of x, then equation 1 becomes d by dx. Okay, so now we've got r of x on the left-hand side and the right-hand side, but we're looking at the left-hand side of equation 1. And we've multiplied r of x times dy dx plus p of x times r of x times y. And we basically said that if we set r of x to be this, then it collapses to product rule. It's the simplified form. That becomes r of x times y is equal to, now remember, we multiplied equation 1 by r, so we have the q of x, and then we have r of x. Okay, and you can solve for, you can multiply both sides of equation 3 by dx, and then you get d r y equals q of x, r of x, dx, and then you can integrate, and then the integral of dry is just ry, and basically is equal to integral of q of x, r of x, dx. We don't know what that is just yet. And then if you really want, you could say y equals 1 over r of x, q of x, r of x, dx. Okay, now this is in terms of, what I showed you just now was in terms of x and y, but our problem is in terms of A and T. So basically, X in our problem is replaced by T. Y is replaced by A. Okay? So if you want, we can put our equations in that form if that's easier. But the first thing we need to do is we need to put our actual problem into the form shown in equation 1. Okay? So basically what we need to do is we need to take dA by dt. I'm going to bring the ka of t over to the left-hand side equals r. I'm going to say ra instead of r add. Okay, I'll let me make it like that, less to right. Okay, now we're in the form, right? We're in the form that we're looking for, because a is y, a of x if you like, and x is t. So now we can just follow. If you want to rewrite the equations, it's, see number 2? 2 is r of t equals e to the integral of p of t dt, right? And then 3, y is a of x, so it's a of t. A of t, 1 over r of t integral q of t r of t dt. This is basically it. We need to solve for the integrating factor and plug it in to our equation. So what do we have? This guy right here is our p of t, and then ra is our q of t. It plays the same role, basically. Okay, so we can now solve. So 2 is r of t is e to the integral of k dt, and that just becomes e to the kt. There's a plus c, but remember r of t applies to both sides of the equation. Okay, so we can any constants will divide out from both sides. All right, awesome. So we've got r. So now let's go right to the solution. A of t is equal to 1 over e to the kt integral. Now q was ra, right? And r was e to the kt dt. Okay, so we're ready to solve here. R of a is a constant, so what I'm going to do here, let me just pull it out. R added over e to the kt is the result of this integral. What's the integral of e to the kt? Well, it's 1 over k e to the kt plus some unknown constant. Awesome. Okay, let's multiply through. So what we can do, this becomes ra over k plus ra times c e to the negative kt. Okay, that is a t. Awesome. So what do we have from our previous solution? We have this. So the ra over k, and then yeah, the c could be a negative. That's actually fine. Here, let's go back to compare. I'm gonna grab the old one. The old one is here, and the new one is here. The old one has, okay, let me just write it in the same order. So we got ra times c e to the negative kt plus ra over k. And up here we have negative c over k. Well, the constants can be, what I can do, let me make this c naught, just to make life nice and easy. And what we're going to say is let c equals negative c naught. Okay, So then this becomes negative RA C e to the negative kt plus RA over K A T. And when you compare, now they're not yet exactly the same because we still have the K. Okay. However, since C is arbitrary constant, okay, and K are arbitrary constant, so negative C over K and negative RAC, this is just a constant. I'm going to call this C3. I'm going to go up here. I'm going to call this C3. It's arbitrary constant, right? So quite literally, what I can do is I can say that A of t equals C3. Okay, I can even say negative RA. Makes no difference here. E to the negative KT plus, now RA over K, we'll call that C4. Okay, so A of t okay, is, now we can change these numbers. I can call this C1 now if you like and call this C2. It makes no difference. And I can go up here and I can edit this to C1 and call this arbitrary constant C2. And you can see that they're exactly the same. Okay, so again, you can go, we can have it in lawn form if you like. So this equation up here, because the solutions are the same, okay, you can also use the lawn form of the solution, of this general solution. So this also applies whether you go, regardless of which approach you take, you're going to arrive at the same solution. You can have it in lawn form, or you can have it, see, these are general, let me write this down, general, you should really zoom in here, general solution. This one is in lawn form. So regardless of the approach you take, you're going to get the same result. And in order to determine K and C naught, or C1 and C2 and K, you basically need to use the initial values. Okay, I don't want this video to get too long, so I'm going to stop here. But basically, as long as you have enough initial values, you can solve for K, the K's and the C's. Okay? All right, thanks. I hope you enjoyed this video.